Hello and welcome once again for another thermodynamics example problem. This one will be dealing with thermal conductivity. Okay, so I'll start with the problem. The wall of an industrial furnace is made of 20 centimeter thick fire clay bricks with a thermal conductivity, of 1.7 watts per square meter. The inner surface of the wall is maintained at 1000 degrees Celsius. Determine the outer surface temperature when there is a heat loss of 1500 watts through a wall of 0.5 meter by 1.5 meter. So this might be the 0.5 meter, and this is probably the 1.5 meter, right? And the inner surface is over here, so that's this one, and the outer surface is here. So the assumption here is that the heat transfer always goes in the direction where the temperature is decreasing. Okay, and that's actually the reason for this negative sign here. So in the direction of decreasing temperature. Now we have all of the things that we need, obviously. The first thing is kappa, which is the thermal conductivity. That's this thing here. It's 1.7 watts per square meter. We also know that we have a heat loss of 1500 watts, which is that thing right there. This gives us the area. So this is going to be here. And we also know the L for the brick, which is 20 centimeters. So if we do a conversion here, 20 centimeters is the same thing as, well, we know 1 meter is equal to 100 centimeters. So we can use that as a conversion. 20 centimeters times 1 meter per 100 centimeters. So we get 0.2 meters. Now we've made all of the conversions that we're going to need to, so we can actually start substituting in. So Q dot X is 1500 watts. Now we have minus kappa here. Kappa was 1.7 watts per meter Kelvin. Times T2, which we don't know. That's what we're looking for, right? We're looking for T2. So T2 minus T1 was given as 1000 degrees Celsius, and so we should convert this to Kelvin here to deal with absolutes. Although the difference doesn't end up mattering, but we are looking for an individual temperature, so we do need to convert in that case. Since we're only looking for this piece, we are going to need to convert T1 here. So T1 is 1000 Celsius plus 273.15 to get us to Kelvin. So we get 1273.15. And that whole thing is going to be divided by L, which was 0.2. Now we can rearrange this, of course. So I'm going to take T2 and move it over to this side. So we get 1.7 watts per meter times Kelvin divided by 0.2 meters times T2 is going to be equal to 1, 2, that's gonna, well, let's do that multiplication out first. 1.7 watts per meter times Kelvin divided by 0.2 meters times T2. Oh, sorry, not times T2, times 1273.15. Notice that the negative signs are going to cancel each other there. We have minus 1.7 and minus 1273.15. So those will cancel. And then we have to subtract off the 1500 watts. I did this because I wanted to get T2 by itself. Now, of course, I can divide through by that 1.7 divided by 0.2. So T2 has to be equal to 1273.15 Kelvin minus 0.2 meters divided by 1.7 watts per meter times Kelvin times 1500 watts. Now notice that the units here are going to cancel. The meters, those are going to cancel. And then this is, those are going to be square meters. I forgot one term actually, didn't I? I forgot the area. So I need to multiply that over here. Which means the this is going to come down here. There we go. That'll fix my problem there. Now I get everything in the nice correct units. So those meter, this ends up becoming meters squared. That cancels with that. And so what we're left with is kelvins, which is exactly what we want. And so now we can subtract that off. So we need to do 1273.15 minus 0.2 divided by 0.75 times 1.7. And that's all multiplying 1500. And what we should find is that this gives 1037.856, if I just round to that point, Kelvin. So let me write that out. Oh, I think I did. There we go. And that's it for this problem. Hope to see you again soon.